So here we have a circumstance of a car entering an on-ramp onto a freeway. So there's a metering stoplight, so it begins from a speed of 0 and it accelerates at a constant rate for 20 seconds. And then after that period of 20 seconds, the car is traveling at 30 meters per second, and then it's going to travel at that speed for another 30 seconds. And so we want to represent this situation on a velocity time diagram, and then we want to determine what's the acceleration and what is the total distance that the car travels. So first thing about these diagrams, we don't have to draw them necessarily to scale. A conceptual framework for us to work with is just fine. So we're going to be keeping track of velocity in meters per second along the y-axis, and we're going to be keeping track of time in seconds along the x. So we definitely want to make sure that we've labeled those. And so if we go back to that information, we have constant acceleration for 20 seconds until we reach a speed of 30 meters per second. So that means I'm going to have a diagonal straight line representing that change in velocity. So up here I can label this as my 30 meters per second, and that's going to happen over a period of 20 seconds. And then we're traveling at this speed for another 30 seconds. So that means our velocity will not be changing, so we'll just have a horizontal component there. Then I'll just drop a perpendicular down to indicate that this happens 30 seconds later for this problem. So that means that's going to be at 50 seconds that we're going to reach that spot. So the first thing that we wanted was the acceleration, as it says here. So we're looking for the slope of that line. So acceleration is going to be the change in velocity over the change in time. So my change in velocity is that 30 meters per second, and then my change in time is that 20 seconds. So here we will pay attention to some significant figures as we do our calculation. So we're only going to have 2 sig figs in our answer. So we're going to have 1.5 meters per second squared as that acceleration. So we're just finding the slope of that diagonal line during that acceleration period. And then for the total distance that the car travels, it's going to be everything. We've got this segment here as well as the segment at which it's traveling at a constant rate. So we can approach it in a couple different ways. We can find the areas of those 2 figures individually, the triangle and the rectangle, or what we can do is we can go ahead and find the combined area of that figure, where I've got this as my base 1 and this is my base 2 of a trapezoid. So my distance in this case is going to be 1/2 times, let's call this base 1 and this one base 2. So base 1 plus base 2 times the height. So my distance is 1/2 times base 1, that's going to be that top segment there, so we know that that's a period of 30 seconds, plus base 2, so we see that that's the entire 50-second period of time from start to finish. And then our height of this trapezoid is the top speed at which we're traveling, so that's our 30 meters per second. So if we follow our order of operations here, we add these 2 together, we've got 80 total inside the parentheses there, times our 30 on the outside. And so then if we continue on pushing buttons on our calculator, and we can see we're going to be rounding off to 2 significant figures because of our 30 that's there that only has 2 significant figures. We're going to have a distance of 1,200 meters. And I'm going to write it like that. That is with 2 significant figures. I could write it in scientific notation if I wanted to. I just definitely don't want to include that decimal point there because that would indicate 4 sig figs instead of just the 2 that were allotted. So here we have a second example where we will be using a velocity time diagram. So we have the same units, meters per second and seconds, as our 2 labels on our 2 axes. This time the information that we're given is a little bit different. So at first we're told that our car accelerates at 5 meters per second squared until it reaches a top speed of 20 meters per second. So with a linear acceleration, what that means is the slope of this line is going to be 5 meters per second squared, and that we're going to top out at 20 meters per second. So then we're told that we're going to continue at that speed for 400 meters. So again, that's a distance. We're keeping a constant speed, so that's why I have a horizontal line there. And so that's going to be for a distance of 400 meters. So that's the area underneath the curve. So velocity times time is going to give us area. So that period of the car's travel is going to be 400 meters. And then with a red light up ahead, the car starts to decelerate until it reaches a stop. And so this time we're decelerating with a slope of negative 8 meters per second squared. And so we've got everything represented on the graph as we went. And so now we're asked how long is the car going to take to get from one stoplight to the next. So we're asked for this period of time along our x-axis. And then we also want to know what the total distance traveled is going to be. So we'll take a look at this problem with 3 distinct segments. There's the acceleration phase, there's the period of time where we're traveling at a constant rate, and then we have the deceleration phase. So let's focus on part 1 here. So again, acceleration is change in velocity divided by the change in time. Unlike the previous question where I knew the velocity and the time and I was calculating the acceleration, this time we know the acceleration is 5 meters per second squared. We know what that final velocity is, so we've got a 20 meters per second up here. And it's the time of this first segment that we have to try to figure out. So if we solve, hopefully without too much difficulty, we're going to find that the period of time here is 4.0 seconds. Just swap the t1 and the 5 meters per second squared, divide 20 by 5, and we get that 4. So that's our time for that first segment. And then for the distance that's traveled, remember distance is the area underneath the curve, so that's going to be the area of this triangle here. So I'm just going to go 1/2 times base times height, which in this case is going to be 1/2 times the base, which is my 4.0 seconds, times the height, which is my 20 meters per second. And so if we multiply that out, we get a distance of 40 meters, again with 2 sig figs based on what we see in the problem. So we've got our information for part 1. We'll switch to red here for part 2. We already know what that distance is, so we just have to figure out what that time for that stretch is. So for part 2, we can say that distance is equal to rate times time. We'll use a d2, r2, and t2 there. So we know that that distance is 400 meters. We know that the rate at which we're traveling is that 20 meters per second. So the question becomes, what is the length of time at which we're traveling at that rate? So if we divide, we can find that t2 is equal to, again, to the appropriate sig figs, 20 seconds. And that's to the nearest whole number. And then we already know the distance. And so then finally, if we go to green here for segment 3, the deceleration phase, so we're going to have to approach it the same way that we did the first phase of our journey. So we've got acceleration, or deceleration in this time, is going to be that negative 8 meters per second squared. That's going to be equal to our change in velocity, but now since we're going from 20 meters per second to 0, that's going to be negative, so our positive and negative signs are going to work out, and then that's going to be divided by this length of time for the third segment. And so eventually, if we just switch the t3 and the acceleration, we're going to end up with a time of 2.5 seconds. And then for the distance, if we just scroll down a little bit, our distance for this third segment of the trip is going to be 1/2, again we have a triangle, times the base, which is going to be that 2.5 25 seconds times the height, which again is our 20 meters per second, and so we get a total distance here of 25 meters. So for a grand total, if we add up our 3 times, we've got this 4, we've got this 20, and we've got this 2.5, but we're going to have to round off to the nearest whole number after we add all those because of our significant figures rules. Our total time in this case is going to end up at, rounding off to 27 seconds. And then for our total distance that's traveled, we've got the 40 meters here, we've got the 400 meters that we already knew from the given information of that middle segment, coupled with this 25 meters. All of those are to the nearest whole number, so if we add those together, we'll get a total distance of 465 meters. So again, these diagrams can be a really handy way of relating acceleration, velocity, distance, and time in a visual representation that makes it easy for us to see how those numbers relate and to calculate for some of the missing information given some other.